know, when we're thinking about right triangles, there's actually a very special theorem that we could actually use to prove that two right triangles are in fact congruent. Sometimes it actually comes in handy, saves a little bit of time. So if we invest some time now to prove this theorem, namely the hypotenuse leg theorem, it's called, then we will always be able to use it. So let's work a little bit hard now, and then never have to work hard again in this direction. Let's check it out. So the challenge is to prove the hypotenuse leg triangle congruence theorem. And here it is. It says that if the hypotenuse and leg of a right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are automatically congruent. And we call this HL for hypotenuse leg. So let me set this up, and then let's think about how we might want to go about proving this. So let's in fact assume that the hypotenuse here is congruent to the hypotenuse here. Of course, those are the sides that are opposite the 90-degree angle. And let's take a leg, and it could be either leg. I'll just pick this one. Let's take this leg and say it's congruent to this leg. So all we're giving it is hypotenuse and leg. So the hypotenuse here is congruent to the hypotenuse here. This leg is congruent to that leg. And now that with just that alone, and knowing the right triangles, I want us to argue that in fact these two triangles are congruent. So how to go about this? Well, let's just think through this first before we start writing anything down, and think through how we might want to proceed. In fact, let me give some labels to these various lengths, because I'm going to use the lengths here. So opposite the C side, I'll call that length little c, I'll call this little b, and I'll call this little a, and I'll call this little f, I'll call this little d, and I'll call this little e. And so those represent the lengths of the sides. Well, we know something about right triangles, and we better use it at some point, which is that a squared plus b squared equals c squared, namely the Pythagorean theorem. And similarly, I know that d squared plus e squared equals f squared. And now let's just think through it together and see the end result. Well, check it out. We know that A must equal D since these sides, these lengths are congruent, they have the same length. So this number and that number are the same. So those are the same number, that's good. And what do we know about C and F? Well, C and F, well, since this segment is congruent to that segment, these must have the same length, so C and F must be equal. So C and F are equal. Well, check it out. If these guys are equal and these guys are equal, the only way that this number plus this number could equal that number, and at the same time, this number plus this number equals that number, these are equal and these are equal, these must be equal. So B and E must be equal. And then if they're equal lengths, that means these two sides are congruent, and then I can have the two triangles being congruent by side, side, side. So there's the whole proof in a nutshell. We're going to use the Pythagorean theorem. That's the key. All right, so let's start writing things down and seeing how it goes. The logic, the hard part to me, is all done. Now it's going to be bookkeeping to make sure that we're rigorous. So where do we start? Well, we start at the beginning. If we're going to use the Pythagorean theorem, we better have right triangles. So remember, these two triangles are right triangles, and that was part of the given. So we're given that we have right triangles. Now, by the Pythagorean theorem, we know that a squared plus b squared equals c squared, and d squared plus e squared equals f squared. And of course, that is literally just the Pythagorean theorem happening twice. Now, what else do we know? I know that AB is congruent to DE, because we're assuming that. That's our assumption, that the hypotenuse here is congruent to the hypotenuse here. And so what does that mean? It means that this length, AB, is going to equal this length, DE, or namely that C equals F. So this is just literally what it means to be congruent if you're a segment. You have equal lengths. All right, so what does that mean? Well, now we're just going to do some algebra that I kind of talked over here. Certainly, if C and F are equal, then if I square both sides, they'd still be equal. So therefore, C squared is equal to F squared. And that's nothing more than just squaring both sides, so that's not a big deal at all. And so now what I can do is I can come back to here, step 2 and 3, and see that since C squared and F squared are equal, then in fact, this sum must equal that sum. These guys we see are now equal. And so I see that a squared plus b squared must equal d squared plus e squared, and that literally is just the transitive property. Since I know that these two things are equal, and this equals one, and this equals the other, then in fact they must equal themselves. Okay, terrific. Now, what else do we know? Well, we know that BC is congruent to EF because that was the leg that was congruent. That was part of the given. Remember, it's called hypotenuse leg for a reason. The hypotenuse of each are congruent to each other, and we have a leg from each that's congruent. And what does that mean? It means that the length of these segments are the same, which I'm calling A and D, and so that's just definition of what it means to be congruent segments. And of course, what do I do now? Well, if A and D are equal, then in place of D here, I can put in A. So here I see D squared, and so I could write this as A squared because A and D are the same value. So check out this line and look at this line. Same, same, and now I replaced A with D. I'm sorry, D with A. And so now I've got the D replaced by A, and the rest is the same. And so that is literally just substitution, so it's no big deal at all. But now, what can I do? I can conclude that B squared must equal E squared because I can subtract A squared from both sides. And so if I do that, I use the subtraction property. How did I get a little mark there? I don't know. It's a little dirty. Okay, and now, of course, if I see that B squared equals E squared, that must mean that either B equals E or B equals negative E. But look, B and E are lengths. Lengths can never be negative. So these are both positive values, and I know their squares are equal. If their squares are equal and they're positive values, then in fact they must be equal, which means that this length equals that length, and that's just taking the square root of both sides, which we're allowed to do since everyone's positive. And since those lengths are equal, it means that these corresponding line segments are congruent. And so after all of that, I'm allowed to do this. Boom, 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 boom. And now we're done, because I see side, 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 congruent to side, side, side. And so in fact, these triangles are in fact congruent by the side, side, side theorem, or by S. So just going through all these steps, look, that's a long proof, 14 steps. But now, we never have to return to these steps again directly. Whenever I have two right triangles, and I see that the hypotenuse on one is congruent to the hypotenuse of the other, and one of the legs of one is congruent to one of the legs of the other, we can apply all of this automatically and say, by HL, or by the hypotenuse leg triangle congruence theorem, I know these two triangles are congruent. And what was behind the scenes here? What was behind the scenes here, of course, was side, side, side. The side, side, side rears its head in a variety of unusual places. Now, as a consequence of that theorem, we have at our disposal the hypotenuse leg congruence triangle theorem, which tells us that, in fact, if I have two right triangles and the hypotenuse are congruent and a leg are congruent, then in fact those two triangles are in fact congruent. Have fun using the hypotenuse leg theorem in your life, and I'll see you soon.